Yeah, we moved around Norway on, yeah, Norwegian fjords. Fjords.
All right. Well, I think we're ready to get started. So thanks everyone for coming out to today's Exoplanet seminar. And I'm going to turn it over to Teresa to introduce our speaker Atul today. Take it away, Teresa.
Hi, everyone. Today I'm introducing Atul Mohan to give a speech. He is from Heliophysics 670, and he specializes in multi-wavelength solar stellar observations with an expertise in radio millimeter interferometry techniques. He obtained his PhD in 2020 from the National Center of Astrophysics in India. And then he did his first postdoc at the University of Oslo from the Rosalind Center of Solar Physics, and he transferred over here to NASA Goddard in the Heliophysics department, where he is a postdoc working with Nat Gopal-Swamy, and he's working with the SDO data. And so an interesting fact about Atul, he loves to travel, and his favorite place to travel was and see the fjords of Norway. So welcome, Atul.
Great introduction.
Thank you, Teresa, for that intro. I'm audible. Yeah. Yeah, so thank you, organizers, for giving me this opportunity. So I'll talk about exploring activity across the cool main sequence stars using sub-terahertz imaging tomography. So my prime expertise is in, like Teresa mentioned, radio millimeter imaging techniques, and also doing science with it and combining X-ray to, optical observations around. So, okay. So to start, since it's an exoplanet crowd mostly, so why would you care about stellar activity? Because stellar activity is your main villain. So cool stars primarily host most of the exoplanets you see out there, especially the Earth-like exoplanets in the habitable zones as we know it. And when you look at these cool stars, starting from G to M type, they are, as you go to cooler and cooler stars, they are more abundant and they live much longer, giving you more opportunities to experiment with life forms and have like habitable worlds. But at the same time, when you look at the X-ray flux and high energy particle flux, they actually produce copious amounts of X-ray emissions and energetic particles as you go to lower and lower mass stars. So we need to understand this stellar activity to better understand which would be a good host, basically. So coming to the cool stellar atmospheres, we can, as we know it, it is actually well stratified, starting from photosphere up to chromosphere and extending out to corona. And this is a snippet from the sun, basically. So you can see there is the photosphere, which is the lower or the outer, the first atmospheric layer, which is relatively at a lower temperature. And as you go to higher and higher atmospheric layers like chromosphere and corona, the complexity of the magnetic field, as you can see, it increases, giving rise to these flaring events, which are happening across these upper atmospheres from chromosphere to corona. And also, interestingly, the temperatures also keep steadily rising as a result of this magnetic activity. Now, this is a picture from the sun, which is a G2b star, and this is the 1D atmospheric structure of the sun as you see it. So in the x-axis, it is actually the pressure, or you can think of it like a scale height. So the higher the pressure, you are actually much deeper into the atmosphere. So starting from photosphere, if you look at it, the temperature initially starts dropping. But then as you go to higher and higher atmospheric layers, there is a steady non-thermal heating processes which is happening because of the increasing magnetic activity in the chromosphere, which does not let the temperature actually fall dramatically. And after a point, this in the upper chromosphere, it actually starts increasing. Now, when you look at even the M dwarfs, we can see that there is a similar trend. Right. So across cool dwarfs, there is a similar atmospheric heating trend that as we know it, and we have observations from the sun in a spatially resolved manner, and we have been exploring it for several decades. So the takeaway is that the picture of this enhanced activity and increasing atmospheric as you go up the increasing atmospheric heights is similar across the cool stars. And now, how does all this activity rise? This is because of the subsurface convective motions, which basically turn and twist your photospheric magnetic fields. This is a typical photospheric magnetogram, which you see here from the sun. And as you can see how the subsurface convection kind of turns the magnetic islands around, and these are basically opposite polarity magnetic fields. And this is how the stress builds up in there. And the active regions, which are which basically links these magnetic islands, as you see here in this cartoon, is constantly twisted and turned because of these motions, building up enormous magnetic stress, which often releases in the form of reconnection events, as you can see here. So where new field lines form, and in the result, they actually dump enormous energy in the local plasma. That's what we call reconnections. And when you look at the scale of these reconnections, they can happen at a few hundred kilometers up to like 10,000 kilometers, and causing these minor spicule jets to massive X-ray jets that you see in the sun. And when they happen across arcades of such magnetic structures, you can have these violent eruptions at a larger scale, which is usually called the coronal mass ejections or the CMEs. Okay, so like we saw, so it's actually these magnetic subsurface convective motions which build up the stress and strain, and then across the atmospheric layers, you basically heat the plasma and cause these flares, increasing the temperature and magnetic complexity in the actual atmospheres. And combining all these different flares which we have observed primarily in the sun, there is something we have which is called a standard flare model, which basically summarizes all these events. So first, like I mentioned, there is this magnetic loop dynamics, which is caused by these convective motions, which build up the stress. And then there is this reconnection, which accelerates the particles, which you see in this cartoon here. There is this reconnection, which is driving these bidirectional electron jets into the upper atmosphere as well as to the lower atmosphere, heating up the lower magnetic loop structures and also the higher lying plasma structures. So the this initial impulsive phase is usually predominantly seen in the radio emissions from centimeter to meter wave band emissions, and also when they hit the lower lying loop structures and when they hit the bottom atmospheric structures, you see basically the hard X-ray emissions and the microwave emissions. And after this impulsive phase connected to the reconnection, you have basically the gradual phase, which is the heating of the plasma structures which are involved, which is usually seen as H alpha continuum, or which is seen as a soft X-ray emission, and also emission across several spectral lines. So this is the standard flare model, which we have come across, which we have compiled with the years of solar observations. Now the question is basically like, and I called it the standard flare model. How standard is it if it is just the sun, right? I mean, so if we look at the flares across other stars, we basically ask the same question. So how valid is this? That do we have an impulsive phase and do we have a gradual phase? Do we see the similar thing? Yeah. So roughly across all the stellar flares, you do have this impulsive radio or hard X-ray continuum, and then there is this soft X-ray heating. So it does roughly correlate. And then if you look at, there has been also cases where we have seen H alpha Doppler shifts from several stars, which signifies some sort of outflows. And also we have seen in X-rays, for example, here, this is Proxima Centauri. There is a strong X-ray flare, and post-flare you see there is a dimming, right? And similar dimmings have been seen in the sun when you have basically a massive plasma, which is basically outflowing and then which obstructs your corona. So that's when you have the dimming. So we do see such signatures of reminiscent of this standard flare model across other stars too. But then when you come to the stellar populations in general, and when you ask the question like how, if you plot B minus V or effective temperature of the star versus the period, you do see that the stars actually form two different populations, which we call the I and the C. The C branch is basically composed of fast rotating young stars, which have a lower period. And then there is this I branch stars, which are basically the slow rotating old stars. So as we know now, the stars basically start as fast rotating high angular momentum objects, and they slowly migrate to the I branch. So there is basically a bimodality in this population. So the question is basically that, okay, the stars do have this different atmospheric structure and different activity characteristics when you look at this period T effective plane or period B minus V plane. So how does it affect their nature of the activity as well, right? So now coming to the motivation, why do we care? So as we know that this has been a fundamental question, like which humanity asked itself, basically, that are we alone in this cosmos? Is there Earth Sun twins out there, or something similar to what we have here, which has been hosting a successful biosphere for long? So to understand this, we should first understand solar activity well, and we have to make benchmark models which can be extended to other stars. For example, this is a work which we recently did, where we looked at all the CMEs in the sun, and we looked at the radio emission, which is basically from so-called type 2 radio emission, which is closely associated with CME shocks. And that create a unique spectral signature in the radio band. And we used all those observations, and we looked at the radio flux, which is LR, which is a sun as a star radio flux. And this is LX, which is a sun as a star X-ray flux during the same event. And we showed that the LX and LR combined with the VCME square, which is basically the kinetic energy proxy for the CME, right? Which is going into the interplanetary space. If we combine these three, we do get a clear correlation between connecting these sun as a star LX and LR, and from which we can directly derive the unknown CME speed. So since these are all sun as a star parameters, LX and LR, and VCME is the only spatially resolved observable, using extending this to other stars is easier, and we can directly derive the CME speeds. So we need more of these kind of sun as a star benchmark models. And the other way is also that we cannot just rely on just the sun as a star. So we should also look at other stars in a broader picture across the cool main sequence, and then compare and contrast, so that we know where do we sit and where are the others, right? So for that, like I mentioned, because activity is a cross-atmospheric phenomena which evolves right from upper photosphere into the chromosphere and evolves into the corona and interplanetary space, we need a tomographic exploration strategy, which systematically covers activity across the chromosphere and shows us how it evolves into the corona, right? Now that's where bulk of my talk would focus on, and why sub-terahertz band is interesting here. So when you come to the radio band, like I mentioned, in the impulsive phase, radio emissions have been extensively explored even in sun and stars, and because it is very sensitive to the electron beams. So if you look at the corona of any star in general, so, and we ask the question, basically any cool star, I mean, if you ask the question basically like what is the local plasma frequency and local gyro frequencies, they all fall in the centimeter to millimeter range. So that's the interesting and the exciting part about the radio. So any kind of plasma instabilities, flares or shocks which are driven in these coronal layers basically cause wave and wave particle resonant interactions at the local plasma modes, right? And the local plasma modes basically fall in the radio band. So you are very sensitive to even slightest of the perturbations which are out there. So the major emission mechanisms in the radio falls into two categories. One is the electron cyclotron maser emission, which is a bright coherent emission which happens when your local plasma frequency local plasma frequency to gyro frequency is less than 3. So the emission primarily occurs at the gyro mode, so the gyro frequency mode. And if your gyro frequency mode is in your radio band, then you basically see that emission, right? And the other one is basically if the emission region has a very high plasma frequency in contrast to its gyro frequency, the emission primarily originates at the local plasma frequency. So in these, how would you separate these two emissions? It's primarily based on polarization. So the electron cyclotron maser emission is a usually very highly polarized emission, which can hit close to even 100%. But from the extensive solar observations, we know that the plasma frequency emission is affected by near source scatterings, because there is a lot of density fluctuations in the regions, which will also cause fluctuations in the local plasma frequency as well, right? So which will cause some sort of depolarization in the emission. So you don't usually hit very high plasma frequency, very high polarizations in those cases, at least in the sun. And another interesting thing is also that the coherent emissions, since this is resonant emissions, since this is born out of some sort of wave particle interactions, they are highly beamed. Unlike, it's not a 4pi emission, it's like a pre-electron maser if you want to think about it, right? So they are going to be highly beamed. So if you can do spectroscopic imaging in the radio band, what we can basically do is like we can basically exploit this idea that this is basically these emissions are basically happening at local plasma frequency, and since local plasma frequency or gyro frequency is a function of height, you can basically track the emission or track the propagation of these instabilities or shocks across the corona just by doing a spectroscopic radio emission tracking. So now coming back to the standard flare model. So, and when you ask the question of like what are the CME associated radio bursts which you see in this or which you can expect from the standard flare model, that is basically these three ones. So which are the type 3 radio bursts, which are often associated with these open magnetic field lines which carry these electron beams out into the corona. Since they are freely propagating across these open magnetic field lines, they are usually pretty fast, and also hence their drift rate in the frequency plane would be very fast. So that's why if you look at the emission from these energetic electron beams, which are along the open magnetic field lines, you can see that they drift very fast in the frequency plane. At the same time, there is the other emission, which is because of the CME shock accelerated particles, which is from these shock fronts. We call it the type 2 radio bursts, and they move at the rate of the shock, right? So they are, so they basically have a nice frequency drift in your dynamic spectrum like this. And then what you have is that these energetic particles, which are hitting into your post-eruption arcades and the other magnetic loop structures, which are the plasmoid structures which are moving, they usually generate these so-called type 4 radio bursts. Now, the characteristic of this burst is that this is band limited. Why is it band limited? It's because it's associated with the post-eruption arcades, right? They have a fixed height scale, right? So they cannot extend beyond a frequency. And because it's dissipated by these energetic electron beams, which are coming and impinging on these loops, they last for some period, which is usually a few hours, and they are band limited because it's in the loop. All right. So these three characteristic bursts are commonly associated with almost nearly every CME you can see. So like I mentioned, the type 2s are with the shocks and the type 4s are with these post-eruption arcades. And if you ask the question of like, when you take all the solar energetic particles, which radio bursts are more commonly associated with the solar energetic particles, which is also of importance to our planetary science, right? It's the energetic particles and the high energy radiation which affects the atmosphere. So if you ask that question, and then if you plot the different bands starting from decimeter to kilometer band, decimeter, meter, decameter, kilometer, like that, and ask the question that, okay, what is the mean CME speed associated with these different types of radio bursts which I introduced, like the type 2, type 3, and the type 4, you can see that the type 4s are very commonly associated with high flare class, high X-ray flare strengths, and also high median CME speeds. So very fast, strong flare associated CMEs are usually mostly associated with type 4 radio bursts. So there is a high correlation there. Okay. So now hence, and also if you look at the band, the decametric heterometric band is mostly associated. If you have a type 4 radio burst extending down to that is mostly associated with a very strong CME out of all their other radio bands, right? So we need to understand these DH or the decametric heterometric type 4 radio bursts. And the interesting thing is that the decametric heterometric band is in the 1 to 14 megahertz band, which is not observable from the Earth. And hence, being at NASA, we are all excited. This is only from space. So, now I work with Gopal on the stereo and wind waves missions, which has this radiometer and which can basically give you this kind of decametric heterometric radio band dynamic spectrum 24/7 when the satellite is viewing the Earth, viewing the sun. And the other interesting thing about the stereo mission is also that these are twin satellites, which is not actually locked to the Earth. It is actually circling the sun. So at any given time, you have radiometers associated with wind on the Earth, and also you have others with, on the stereo, which is giving you a different vantage point of the same event. Now, this is also exciting because I said that the radio bursts are inherently beamed. So the question would be that how would the same event look like in these different vantage points, different line of sights. So when we also point our telescopes at different stars, this is also going to be very important. What is your line of sight towards the active region and how does it affect your radio detection, right? So we asked this question and we made this multi-vantage point CME type 4 catalog, combining all the CME events, nearly like 33,000 of them, and then going through all the radiodynamic spectrum and then compiling it. And then we find that the DS type 4 bursts are usually last for 1 hour, which is like 60 minutes, right? And they usually extend typically down to like 7 megahertz, and they are, like I mentioned, very closely associated with fast CMEs, like CMEs more than 1200 kilometer per second speeds, and usually also with halo CMEs, which extend so much that which is so powerful and it extends covering the entire disk of the coronagraph. Okay. Now coming to the beaming question. So what you see here is basically in the x-axis, you have these different events which had multi-satellite, at least 2 satellite observations of the same event. Okay. And the colored dots are just the best viewed event. So the best viewed event is defined as the event which is more intense and also which lasted for long in frequency and time period, right? So that gave the best view to the satellite. That's the idea, right? So now in the y-axis, what you see is the line of sight. So that's basically the line of sight of the satellite towards the active region. Okay. So if you look at like all the best viewed events, they usually correspond to plus minus 60 degrees. So that gives you, because like you see here, like all the colored dots are primarily within that, right? Unless you have a case where you don't have any observation here, when you had 2 observations which are outside of it, then the one which was more closer in the line of sight would give you the best emission. So whenever you had observations within this plus minus 60 degree range or outside, you always find that the best detection is always within plus minus 60. So that gives you the inherent beaming in these type 4 emissions. And when you plan observations for other stars to detect these kind of CME associated bursts, especially the type 4s, better we have to care about this line of sight in choosing the active regions, right? So, okay, now coming to the stellar paradigm. So what is the paradigm in stars with related to the CMEs? So people have been searching for CMEs all along, and we have a lot of tentative observations of this, like I already showed, the X-ray dimming was there. There are also X-alpha Doppler shifts. Yeah, Kosuke is sitting here. Yes. So, but the interesting thing is that there are no CME associated radio bursts, right? So where are they? Okay, so there is this lack of type 2 which has been in the discussion for long. Okay, so people say that, yeah, type 2 may not be happening because these are very active stars, strong magnetic fields like you see here. They are predominantly dipolar. So if you have a strong dipolar field structure which can block your CME from propelling out, or it can give a huge magnetic field barrier at least, then the shock won't form. Even if some outflow happens, it would be not a shock. Right? Okay, fine. So that can block type 2. Type 3s, people would say like there are no open magnetic fields, it's predominantly closed field, right? So if you don't have open magnetic field exits, there is no type 3s. Fine, but where are the post-eruption arcades, right? Even if you have confined flares, there should be post-eruption arcades, right? So there should be type 4s. So that was the question we asked. So we took this interesting star, AD Leo, which is like 0.4 solar mass and which is a very young active star. And the most interesting part is that it has the Zeeman Doppler imaging maps, which gives us a sense for what is a magnetic field structure. And we know that the magnetic poles of the star is oriented around 20 degree along our line of sight. And the interesting thing about these kind of active stars is, like you can see in this picture, the active regions are mostly in the higher latitudes, usually. That's what we know from the optical observations, right? And when you go more towards the poles, and if you have also a good line of sight towards a star's pole, where its active region belt also somehow coincides, right? So you have a better chance of seeing probably these interchangeable connections between the active regions and the open magnetic field lines, which could give you light. And the other thing is that you have a direct observation towards the active region, so you should not miss a type 4. So yes, and another interesting part about this star is also that recent observations by Bellotti 2023 also showed that the star is going through an activity cycle, probably becoming lesser and lesser axisymmetric magnetic fields. Okay, so this is what we usually see in the sun. I mean, we have this 11-year cycle where the magnetic field, the dipolar fields becomes less stronger and more active regions come up, which is when you will have this less axisymmetric field structure. So probably the star is going through that kind of an activity cycle, which is also good for you. The shielding is lower, right? So yeah, so we focused at the star, and then we got the first ever discovery of a type 4 radio burst in a C branch star. Okay. So this is for comparison a solar dynamic spectrum from stereo from one of our catalogs. Actually, you can see this. This happened during a massive solar CME, which was a halo CME, and you can see the comparison with the AD dynamic spectrum here, right? So this is the first time somebody actually got two radio bursts in at the same time, and which looks pretty much similar to solar CME. And this is from a completely non-solar type star. So we model the active region magnetic field for this using the emission mechanism, which we can infer from the level of polarization, that the polarization was nearly 100% in these type 3 radio bursts, and that is possible only if it is an ECME type of emission. And there has been also literature, a lot of literature which suggested that why it should be ECME in these stars, because they are highly magnetized, right? That's the main reason. So based on using that and using our radio observations, we put basically two different models for the active region, which might be producing it. And one model was a simple multipole expansion model based on the Zelotizim and Doppler imaging results, just a simple multipole model. And the other one was basically a solar-like active region model. So we put a solar-like active region structure and then ask the question that what would be the gyro modes in the star, and can we, if given that kind of a magnetic field structure, can we see this emission at these frequencies? Okay. And the answer was surprisingly and excitingly that none of the solar like mean active region models would fit the star. And you would not see an emission at these frequencies. Okay. So that's about the coronal meter wave tomography. And coming to now the other layer, which is the most important layer, which is where it all starts, the chromosphere, right? So we have been talking about corona, but if you want to know the roots of activity, you have to go down to chromosphere. So that's where the millimeter submillimeter emission comes in. So what you see here is basically the emission contribution functions, which is based on a 3D model of the sun for the different millimeter frequencies starting from 33 to 1000 gigahertz. If you ask where the emission heights are typically on average, given the 3D atmospheric model, you can see that the heights, you go to higher and higher frequencies, you penetrate deeper and deeper into the chromosphere. And the emission is primarily LTE at LTE. So it's thermal emission. So you can basically read off the temperature from the fluxes. So we did the same exercise for a 3D atmospheric model for AD-LEO, and the same thing happens. So this is an interesting thing about the millimeter submillimeter band, where you can basically use it like a linear thermometer. So just do a spectroscopic emission and you get the linear thermometer. So we use this idea, we use this quality of this band, and we looked at all ALMA detected main sequence stars. We also ensured that there is no disks or any kind of companion which is contributing to the potential emission which we observe. And going through this extensive exercise, we found actually 13 main sequence stars which are clearly stellar emission from quiescence. Okay, so we also eliminated all the flares. And what you see here is a snippet of that. So you have from the fluxes from multiple ALMA bands, we derive the temperature from simple Rayleigh-Jeans law, because this is thermal emission. And the brightness temperature would be a proxy to the electron temperature directly at these different heights. All right. So if you look at the first star here, it is the A-type star, Sirius A, basically, very famous star. So if you look at the brightness temperature spectrum, you can see that there is a drop in the effective temperature when you go to lower and lower frequencies. Okay, so this is lower and lower frequencies, and there's a drop. Lower and lower frequencies is higher and higher heights. So that means the star has a decreasing temperature as you go to higher heights, which is what you expect from an A-type star, a big A-type star with no atmospheric heating, right? So when you start going to F dwarfs and higher, like not higher, like basically lower mass stars. So you can see that there is a significant increase in the temperature with lower and lower frequencies. And now for comparison, what we have in this dotted line is basically a photosphere only emission model from Phoenix. Okay, so the Sirius A very well aligns with the Phoenix model with a purely photospheric emission, but all others are very deviant from the Phoenix model. So there is significant chromospheric heating, and since we can characterize it with millimeter band, we actually did a spectral index characterization to give, which would be a proxy to basically atmospheric heating gradients, right? So what we did is that we looked at these spectral indices, which are atmospheric heating gradients across the main sequence stars, since we have from A dwarf to K dwarf. Okay, so we find that there is a significant trend from with alpha the millimeter spectral index, and the T effective, which is the surface temperature. And we see that the star somewhere around this 8,000 Kelvin is where all this activity business basically starts in the main sequence problem, right? If you just simply extend it. And these stars have alpha which is less than 0, which basically means that it's a dropping temperature as you go to higher and higher, right? So, yeah. And now the question is like, what about the C branch star AD Leo? So we have been having a campaign with the NOEMA instrument in 85 to 105 gigahertz band, basically the millimeter band. And what we did is that we basically derived the quiescent spectrum of NOEMA, eliminating all the potential flares and everything. And what you see, this spectrum is basically a Phoenix spectrum plus a chromospheric model on top. And the chromospheric model is basically based on observations. So there was an observation grid of UV optical spectrum to UV spectrum of the star, and this is consistent with that spectrum. So it is a chromosphere which is consistent data constrained chromosphere. And that's also why when you go to these higher frequencies, which are like greater than photospheric V band, and here what you see is basically the true flux and the deviation of the true flux with the predicted flux. Okay, so 0 means that it's very good model, right? So here in the photospheric V and above, you have a very good agreement with what the model predicts and what the UV or photospheric spectrum is. And now when you come to millimeter, if all we had from our sun-like stars, the old F2 Z dwarfs were true, this should agree, right? Because this should be from the chromosphere, but it doesn't. Yes, so that's where we are right now. So the C branch stars have a very different chromospheric or chromospheric emission, at least that's what we have from here. So when we look at here, so this is the deviation of the NOEMA fluxes, which is close to 100 gigahertz from the predicted data constrained UV data constrained chromospheric emission. Okay, and now we also calculated the spectral index alpha for the millimeter spectral index for NOEMA, for AD Leo, and we plotted it with our sun-like other sun-like stars. And if you just extend the same curve, we see that the star is way above everything. So even we try to put in the active region filling factors from the Zeeman Doppler imaging, and still it doesn't agree at all. So we suggest that there should be some sort of persistent strong particle acceleration happening even right from the chromosphere and above, which is contributing a lot of non-thermal heating into the star than what we know in our sun or any of those old dwarfs. So yeah, so the final takeaways. Before that, I would like to introduce the future is bright in this sub-terahertz band with the square kilometer array actually coming into the horizon. So during my PhD, I have been basically a solar astronomer. Now also I work with the sun. So the SKAO precursor telescopes were already there. So the SKAO is going to be the most sensitive telescope on the planet if it comes, and it is going to come by the end of the decade, and it will cover from 50 to 15 gigahertz at sub-second resolutions. Okay, so that's the game. And this is a snippet of what kind of imaging it can provide. So this is solar images made with a precursor telescope of SKA, with which I did my PhD actually, and I built the pipeline for imaging as well. So what you see is the sun at every second, and how the non-thermal emission at the active regions basically evolve at sub-second scales. And now with this kind of instruments, we can actually make the active region dynamic spectrum specifically for various regions of the sun. And we can explore, like when you see a whole sun dynamic spectrum, what kind of active region activity give rise to what kind of spatial and temporal variability scales, right? Now, if you see a completely different star, you are basically having an average dynamic spectrum. So we can actually use these kind of tools to kind of separate out what type of activity type would be happening on that star, which is giving rise to these kind of frequency time behavior. So previously, even in the sun, we didn't have this kind of imaging. So, but now with SKA, we have this kind of imaging. And it will also let us explore the stars in our near neighborhood out to like a few hundred parsec easily, and then we can make a better analysis of it, which type of active region is probably causing it and so on. So for a comparison, this is UGMRT, which gave us the ideal dynamic spectrum, and this is our very old VLA. And this is where SK is. So SK is going to be like 10 times more sensitive than that. And in terms of angular resolution, this is where SKA is going to be, and this is almost close to HST resolutions. So, and similarly in the sub-millimeter millimeter band, we have already ALMA and NOEMA, and there is also one at last coming up, which is a 50-meter single dish, which will also help in the solar observations. And with these guys in the millimeter band and with SKA, it's a very good time where we'll have like nearly seamless 50 megahertz to 1 terahertz spectroscopic imaging capability, covering chromosphere to corona. Yes, so this is the main takeaways. The meter wave high dynamic range imaging has let us given us new insights into how the solar and stellar activity evolves, like I have mentioned, and we discovered the first CME associated radio burst in a very DM for the first time. And I also showed you results from millimeter emission in the chromosphere and how the chromospheric activity evolves across the main sequence, and how the behavior is quite different in a case of a young non-solar type AD Leo compared to the solar like stars. And yes, in future we have more powerful instruments coming up. Yes, thank you.
Great talk, Atul. So yeah, we have time for questions. So if anyone online wants to raise their hand, or you can also post questions in chat. And of course, anyone in the room can raise your hand if you have a question for Atul. Yeah, go for it.
Yeah, well, can you go back to the slide where you have like the two satellites observing the same event? And one of them is a stronger signal.
Yes. You mean that type 4 one, right?
Yeah.
This one?
Yeah, that emission beaming graph.
Uh-huh.
So understanding the closer you get to zero, that's
Mhm.
you're in line with the beam.
Yeah.
Right? So I guess I'm wondering on the last event or second to last event, why the one that's like almost on exactly on zero is not the stronger of the two
You mean
observations?
this one?
Yeah.
So this is actually at the
Oh,
limb,
sorry.
right?
Next one over. With the red and triangle, event 46.
Okay, yeah, this one.
Yeah.
Yeah, that this was a rare case. So there was an occultation because of the nearby active region.
Oh,
Yeah.
okay.
So then you can't help it, right?
Sure.
Yes.
Where would you
And
put
I-
in occultation?
So if there are other active regions nearby, right? If it is too close, and let's say like even if you are barely like 10 degree, right? You are seeing through this dense plasma of this active region to reach the other one, right? And versus if you are like, let's say 35 degree here, you will get a better view. right? You don't have anything obstructing your.
I have another hopefully softball. Could you walk me more slowly through your conclusion of like why you wouldn't or why you don't expect to see type 4 emission using the solar model? I didn't quite catch
You mean,
that conclusion. It seemed like an important takeaway.
oh, yeah,
didn't understand.
okay, this one, right?
Yeah,
Yeah, so like I had, okay, so in. Yeah, here I was mentioning these different emission mechanisms, right? So depending on what the condition of the local plasma modes is at your emission region, right? So you can have different types of emission mechanisms. So if at your emission region, the local plasma frequency to gyro frequency is less than 3, usually the mode that is excited is the gyro mode. Okay. So gyro modes are basically the electron gyration modes in the local field. So there, the plasma frequency is or the plasma frequency related mechanisms is not dominant, and hence the polarization fraction can be close to 100%. So in our observations, we saw nearly 100% polarization in those type 3 like features, right? So we naturally know that this is the emission mechanism. So if that is the emission mechanism, given the surface of the star, right, we can ask the question that, okay, which heights this, and this new beam will be in your observation band. All right. And there are also, yeah, I didn't get into the details of it. So the polarization, like the polarization sense was left circularly polarized. That also makes a difference. So we know that basically it's close to the poles, the south pole of the star. Okay, so this was in the sense of the electron gyration. So the observation we did was left circular polarization is what we got, and that's what you would expect if you have a close by south pole. So now so these two adds that, okay, this is one mode of this gyrosynchron, this ECME that we are observing. And now you can, given the ZDI map and the magnetic field extrapolated by those two different ways I extrapolated. So that's where we use the different models. So ZDI gives you only on the surface, right? So now you have to extrapolate it into the corona, right? So you can do it multiple ways. So one way is that I used a solar like active region model. And the other way which I used is the multipole expansion model, which takes in the ZDI results. Which assumes like the same fraction of bipolar, I mean the colloidal and the toroidal. Yeah. So if you do that, assuming that this is from a solar active region in an ECME emission mode, and it is in this and then extrapolate the magnetic field, and then you can ask the question that if this is a magnetic field there, will I see this emission at this frequency? Because that gyro mode should exist, right? Because its magnetic field directly gives you the new beam. So that's what we did. Okay, so given the solar-like field structure, we don't see that frequency mode can give rise to this observed emission.
okay. So it sounds like that was surprising, but I guess for a non-radio expert, is there some punchy way you can describe like why isn't it observable and you were surprised by that? Like you started this, or we can talk offline about this. Sorry, I don't want to derail the Q&A.
No, I mean, the thing is that this has been searched for like over a decade because this is very closely associated with CMEs. And so we have these kind of, X-ray dimming signatures where there is like Doppler shift signatures, but where is the sharp signatures or where is the post-eruption signatures, right? So,
Thank you.
yeah. Without that, you cannot be sure that there is really something accelerating particles across the corona, right? So, for example, you can have a dimming if you just have a bulk flow which goes in through those, larger structures and then just blocks you there. Right? It's not a CME. But if you have something which is extending out, like creating some sort of instability across multi-frequencies, and propagating out, that gives you the sense of propagation. Right? It should propagate out into the interplanetary space, right?
If you go for it.
So just a quick, so I don't fully understand what kind of physical parameter can we derive from the type 4 observation. So that can frequency or duration or intensity or something. So what can we run from that?
So intensity, converting coherent intensities to, what is the local conditions is not possible even in the sun. So that's where in my introduction talk, we were looking at it in a different way, like looking at trying to get correlation curves, like LR versus LX and the CME speed, reconnection flux. So in that paper, we also discussed how you can derive the reconnection flux from just sun as a star, LX and LR. So getting down into the nitty-gritties of how exactly this emission evolves is still an open problem. It's very difficult because you have to know about this, since these are coherent emissions, and that means it's a free electron laser kind of a mechanism. You need to know what is the amplification factor locally for these electrons and what are the wave modes, wave strengths. That's very, very local. Even in the sun, it's not it. So only thing we can say, so that's why we use the frequencies. Okay, and if we have and since we have ZDI and magnetic field extrapolations in the sun, we have even better, right? We can actually do nonlinear force field extrapolations and so on. So we can actually say where these frequencies exist, right? And in the sun, it's much more better since, like I showed in SK and this even in the pre-SK precursor era, we can have actual images to put, the source to the magnetic field map, but here we don't have that. So we can only do it in a 1D sense. So we can say that, like I mentioned, so I start with the photosphere where I have observations and I ask the question, in the corona, does these fields exist? If I assume this extrapolation technique.
So
That's
what
all.
What the physical interpretation of that duration of the type 4?
Uh-huh.
Is it the lifetime of the electron?
Yeah.
or-
That would be that. Yeah, and that was also agreeing here. So like this was also like a nearly 1.5 hour duration type force, which is usually what is seen in the sun. So like the earlier plot I showed, right? The mean DS type 4 duration is around an hour. So all those characteristics are very well matched, and it's band limited. It is band limited. So,
Another thing that if you have a broadband observations, at least at two frequencies, that then you can derive the slope of the distribution, and the slope gonna give you the electron beam distribution. That's that would be at least two, if you have 2 points.
But that would be also in the microwave only, right? If it is
Yeah.
gyrosynchronous, but this is coherent emission is possible.
For gyrosynchronous
Yeah,
transmission,
then
it's
it
possible.
is possible. Yes,
Yeah, for coherence.
it's not possible.
So I have a super complicated question on the waterfall plot here. I'm a pretty big solar expert, of course, but what is a type 1 flare?
That's not here.
Yeah, I see.
Yeah, type 1 is usually, okay, so maybe the last one.
Yeah, I don't know, just, is this new? Yeah, right.
So,
Okay.
I like it.
so for example, this active region, right? This is still bright, right? But if you look at in the X-ray light curves, nothing is happening on the sun. So an X-ray or a UV person would say, yeah, sun is just quiet, but it's not quiet. So this is a type 1.
Okay.
So there is always this constant magnetic field rearrangements which is happening because of the subsurface motion, which can accelerate particles and fill up the loop structures. And so even if nothing is happening in X-ray, you will have a bright radio variability. So that's a type 1.
Gotcha. Thank you. Yeah. Not online. Yeah, if anyone has any questions online, feel free to raise your hand. Yeah, go for it.
I do have one question. I noticed in your last slide, you had mentioned QPPs. Would you go in and do a little bit of that?
So for example, this can be called a QPP.
Oh, that red spot?
Yeah, if you take a lighter, it's a QPP.
Yeah. I see.
Yeah.
Okay.
Yeah.
No question. So since you can do a lot of this from the ground, having trouble tracking all the different observatories that were being used, but we're focused a lot, folks like Allison on launching UV, UV observatories that would monitor these stars. What can you learn if you monitor both from the ground
Mhm.
and in millimeter or radio, and then also in UV?
Yeah.
Have you modeled that or?
Yeah, this stellar observation, I had UV planned. I always do multi-wavelength, but all the time I don't get it. Something won't trigger. Or the NOIMA observations were like, they try to trigger it, but then they said like, hey, the dish is filled with ice. Like, okay, fine. So things like that happen. That's why we didn't have data.
Yeah.
But, and then once we did have not online because I was in Oslo, we have that time thing. So, but then the volcano just erupted and like, yeah, all those things.
That's a
Yeah,
thing,
so-
positive for space tell us if you don't hear a lot. We don't have any volcanoes erupting.
So, but if we had data, yes, definitely. So we could have done this analysis in real time, right?
Right.
So we can now, like I said, the star also has activity cycle and stuff. So now those points are from this year. So it could be from anywhere,
Yeah.
any period of the stellar activity. But if we have real time, then we can really do a better job of this, like fit those UV and get the right fields models. And then say that how much is the chromospheric response. Like the good part about millimeter is like its temperature. It's LT.
Yeah.
So it's not affected by all those spectral line issues of non-LT effects and other.
What extra data do you need to verify this hypothesis, persistent strong particle acceleration?
More data across the millimeter band, I would definitely say, because like there can be gyrosynchrotron extending out to from corona, because these stars are very active in corona, right? So if you have that gyro peak shifted to higher frequencies, this could have coronal influence. So if we have X-ray observations, that can fix it, right? What is
Yeah,
it?
so, yeah, we're talking about from few gigahertz to like, 10, 20 gigahertz, this range for the corona.
Any last questions for Atul? All right, well, if not, let's thank Atul again for a great talk. Thanks everyone for coming out online. I'm gonna end the meeting now. I don't think we have a talk next week, so we're off next week, but thanks everyone for coming out.